All right, guys, so today we are starting kind of a different branch of calculus. We've been doing a lot of derivatives, and going forward in Chapter 4, we're going to be looking at what are called antiderivatives. So instead of finding the derivative of something, we're going to be taking the derivatives and going backwards. So just kind of an introduction, if I look at these functions right here, I've got f prime of x equals 2x, and if I was trying to go backwards to figure out what my original function was, I know that my exponent rule, if I had x to the fourth and I wanted to take the derivative, I'd bring the 4 down, and then I would lower the 4 exponent to a 3. So my x right here is an x, which means in the original function, it was an x squared. And when I took the derivative, I brought that 2 down into the front, and that's what gave me the 2x. So my original function is just x squared, but there was also another number. There was some constant. I don't know what it is because remember, the derivative of a constant is nothing. It's 0. So I would have x squared plus some number. I don't really know what that number is. This second one, the derivative of my function is x. So my original function had an x squared, but when I brought that x squared down and multiplied by 2, I don't have a coefficient anymore. So whatever was in front of my original function, when I times it by 2, it made it a 1, which means that I actually had a 1/2 in the front. And then again, there could have been some constant that went to 0. So my original function was 1/2 x squared plus c. And if we keep this pattern going, f prime of x equals x squared. Well, that means my original function was x cubed. And when I brought the 3 down, whatever it multiplied by just made a 1, which means in the front I had a 1/3 x cubed plus c. And this pattern just keeps going. This one I'm going to rewrite it first. Instead of x squared, I'm going to write it as x to the negative 2. So that's my f prime of x. To get to my original x, I go up by 1, so that's x to the negative 1. But that means that I had to multiply the negative 1 down here into the front, and when I did that, I got a positive 1. So in my original function, I had a negative 1, x to the minus 1 plus c. So that means my original function was negative x to the negative 1 plus c, or I could just write it as negative 1 over x plus c. So the idea here is that you're trying to use what you know about derivatives to go backwards. And if you notice the pattern, when I'm just dealing with exponents, when I have an x, I know that I'm going to have to increase my exponent by 1. Okay, so my pattern, I'm going to add 1 to my exponent. But then when I added that 1, when I added this 1 on here from x squared to get x cubed, my original function, I had to bring that 3 down and multiply it. So I can't just add 1 to the exponent. Then I either need to divide by that exponent, by the new exponent, or I need to multiply by the reciprocal, which is usually easier. So for example, if I have x to the fourth as my derivative, going backwards, I'm going to go x to the fifth, but I either need to divide by 5 or I can do 1/5 x to the fifth. And I think this way usually makes the math a little bit easier going forward when you multiply by the reciprocal. So now here's why things are, well, and then we would have the plus c, of course. And here's why we kind of get stuck with that plus c. When we're taking these antiderivatives, if I look at these g of x's right here, I've got g of x equals 3x squared plus 8, g of x equals 3x squared plus 5, g of x equals 3x squared minus 2. If I take the derivative, g prime of the first one is 6x. G prime of the second one is 6x. G prime of the first one is 6x. So it looks like 6x is the derivative of 3 different functions because they all had a different constant. So when we don't have any initial conditions, when we take the antiderivatives, when we work backwards, we don't know what number was there, so we're just always going to put a c, all right? So what this is going to look like going forward, what you'll see, some different notations and things, is if I've got y prime equals 5, another way to write that is dy dx equals 5. And then if I want to move my dx over, I can say that dy equals 5 dx. Now, if it wants me to go backwards and find the original y function, then we use this symbol right here. This is called an integral. And that symbol is going to be in front. And this would be the integral notation of finding an antiderivative. And you do all the same work. This symbol just tells you that you need to go backwards, that you need to take the integral of dy equals 5 dx. You need to take the antiderivative of that. So over here, the integral, the antiderivative of dy is just y. And over here, the integral of 5 dx, or the antiderivative, remember, if it's a constant, I just have to add an x to it, because that's like x to the 0. There's nothing to divide by, because technically this just is an x to the 1. And then I have my plus c. And I don't know what that is yet, so I'm just stuck with y equals 5x plus c. Okay, so let's get into some rules. Now, most of the time when you're doing these antiderivatives, when you're doing these indefinite integrals, you're usually going to be dealing with exponents. So this idea of add an exponent and then multiply by the reciprocal is pretty much what you're going to be doing over and over and over again. So we've talked about our different notations here already. So now the process of taking these antiderivatives, that's what we call integration. And notice that there's no numbers up here. There's no a or b. There's nothing. It's just an integral symbol. That means that we're taking an indefinite integration. We're not looking at certain values. We're just taking the entire integral of that whole function. So a few notations. Y equals the integral of f of x dx. A lot of times what they'll do is the lowercase f of x will represent your derivative. And when you take the integral, the capital F of x will represent your original function. So a lot of times the derivative will be written with an f and the original will be written with an f, a capital F. Now, my issue with that is it changes all the time. I prefer this method, that if it's a derivative, I like to put f prime. Whether it's lowercase, uppercase, whatever it is, if it's a derivative, I usually will put a prime, but other books, other places, you might not see it that way, okay? And then before we get on to some of these integral rules, if I take the derivative of an integral, that's kind of like taking the division after you multiply, or taking the addition after you subtract, or taking the square root after you square. If I take the derivative of an integral, I just end up back with my original function, which makes sense. I take the derivative and I turn it into my function, but then I take the derivative of my function and I get back to where I started, okay? So here's some basic integration rules, kind of working backwards. If I, over here on the left, this is the rule when I take f prime. Over here on the right, this is when I integrate and I go backwards to find f of x. So when I'm taking a derivative, of a constant, I get 0. So if I take the integral of a 0, I end up with some constant. So going backwards, 0 turns into a constant c. If I take the derivative of k multiplied by x, the x disappears and I just end up with k, a constant. So if I take the integral of a constant, then I end up with k times x plus that new constant. So that's like saying if I were to take the derivative of 3x, that's going to equal 3. So going backwards, if I wanted to know what's the integral of 3 dx, well, going backwards, all I have to do is add an x. But then don't forget your constant, okay? Back to these rules. If I take the derivative of a constant multiplied by my function, we learned that you could just pull the constant out in front and take the derivative of f of x. So going backwards, if I'm taking the integral of a constant times f of x, I can pull the constant out in front and then take the integral. I don't like to do that. I'll show you that in a couple problems. Usually I just leave the constant with my f of x because I'm going to have to multiply it anyway, and it's one less rewrite that I have to do. But you can. You can move the constant out in front and then multiply it back in after the fact. So if I took the derivative of f of x plus g of x, that's just f prime plus g prime. Same thing going backwards. If I take the integral of f of x plus g of x, that's just like taking the integral of f plus or minus the integral of g. And then don't forget your c there at the end. And it's kind of cool because you really only need one c, because technically if I take the integral of f of x, I'm going to get something like 3x squared plus c. And then if I take the integral of g of x, I'm going to get something, let's say, negative 2x plus c. But then when I add these together, that just becomes 3x squared minus 2x plus c. I don't have to put 2c because c is just some constant that we don't know. So we just combine those into a new constant c. So a lot of times that's why, even though we're taking two integrals and adding them together, the constant is still just some two constants added together. C is not a specific value. It's just representing some number, all right? And then the power rule. This is what we've already learned. When I take the derivative, I drop my exponent 1 and times by the exponent, right? So going backwards, if I'm taking the integral and there's an exponent, I add an exponent and then multiply by the reciprocal. So this rule right here is our add 1 to the exponent and then multiply by the reciprocal of the new exponent. And that's a lot of rambling. So let's just start doing some of these. I think the examples go way further than than all these rules. So if I'm looking for the derivative, we'll start right up here with the integral of 5x dx. So I know that this x is going to turn into an x squared. And I already have a 5 in front. But when I turn this x up into an x squared, I need to multiply by the reciprocal of the x squared, which is a half. And then I add c. So this just becomes 5/2 x squared plus c. So that would be my new one. Sometimes it helps to rewrite the problem. Like this one, originally it wants 5 over x cubed. But just like taking the derivative, it's going to be a lot easier if I do the integral of 5 times x to the negative 3 dx. Now when I integrate, this x to the negative 3 goes up by 1, so it becomes x to the negative 2. And I still have a 5 in front, but when I raise this to a negative 2, I need to multiply by a negative 1 over 2. I need to multiply by the reciprocal. So I'm going to times by negative 1/2 and then add c. And to simplify, I just get negative. Now I'm going to move this x to the negative 2 down. So I'm going to put negative 5 on top. And that x to the negative 2 is going to go down on the bottom with my 2. And that's just going to become x squared. So I'm going to write it as negative 5 over 2x squared plus c. The negative 1 up here multiplied by the 5. The 2 stayed on the bottom with the x to the negative 2 when it moved down. So the second one, root 2 times, or integral of 2 times root x. I don't like root x, so I'm going to rewrite that as 2 times x to the 1/2 dx. So when I integrate, this 1/2 has to go up by 1, so it becomes x to the 3/2. And I still have a 2 in front, but because I raised this to a 3/2, I've got to multiply by 2/3. And then I need to add my constant c. So 2 times 2 is 4. My 3 is still on the bottom. And I've got x raised to the 3/2 plus c. And that's it. That's simplified enough for me. You could rewrite it as 4x to the 3/2 over 3 plus c if you really wanted to. You could even rewrite it as 4 root x cubed, all divided by 3 plus c. They all mean the same thing. That answer right there is great for me. All right. Now, integral of 3 sine x dx. So remember, we can move that 3 in front and just do the integral of sine x dx. And if you think about integrating sine, when I take the derivative of something and I end up with sine x, well, cosine turns into sine, but it turns into negative sine. But this is a positive sine. So I actually have negative cosine x. And then the way that I wrote this, I would have a 3 written out in front. And here's why I don't usually like to move the 3 in front. Because now I have to rewrite this as negative 3 cosine x plus c. But I feel like if I had just left the 3 here, if I had just done the integral of 3 sine x dx, I know that the sine of x comes from cosine x, but I have a 3 in front, and I've got a negative. It just saves me a step that I don't always like to do, but you're welcome to move it in front. Just be careful that you write your answer the correct way when you're done. Okay, so moving into, let's do a few more, well, lots more, actually, just with a little bit more interesting scenarios. So the integral of 3x plus 1 over divided by root x. First thing that I want to do is rewrite it. Remember, just like derivatives, we don't like that root x on the bottom. So I'm going to rewrite this as 3x plus 1. And when I move that x to the, well, first of all, that x is just an x to the half. So when I move it to the top, it becomes x to the negative half. I need to be careful not to skip steps here. So I've got a lot going on. I'm going to go ahead and distribute that x to the negative half inside. So this becomes the integral of 3x to the 1 times x to the negative half. Well, you just add those together. So that just becomes x to the 1/2. And then when I times the x to the negative half into the 1, I just get plus x to the negative 1/2 dx. So now that it's split up, instead of trying to undo a power rule, or a product rule, excuse me, instead of trying to undo a product rule, now I just have 2 different functions added together. So technically, I'm taking the integral of 3x to the half, and I'm adding the integral of x to the negative half dx. I should put a dx on both of those. So starting with this one, when I take the integral of x to the half, I need to add 1. So that actually becomes x to the 3/2. And I still have a 3 in front, but don't forget that you have to multiply by the reciprocal of this. So multiply by 2/3. And then I'm going to add the integral of x to the negative half. So when I add 1 to negative half, I get positive half. but I need to multiply that positive, the reciprocal down in front. So that's going to be 2 over 1 in front of the x to the half. And then I've got my plus c. So when I simplify, 2/3 times 3, that's just 2x to the 3 halves, plus 2 over 1 times x to the half is just 2x to the half, plus c. And again, if you wanted to simplify more, you could. You could make this 2x to the 3 halves plus 2 root x plus c. You could factor out the 2, although that would, to me, that just is making it more messy. But you can simplify as far as you need to on the multiple choice, or if it's on the free response, quit simplifying. As soon as you get here, stop. Okay. Integral of 2 sine x over cosine squared x dx. I really like this example because it tells me how much you've worked on remembering your derivatives with trig functions. So the first thing I'm going to do, I have no idea how to integrate it in this form. That's too messy. I've got a function on top. I've got a squared function on the bottom. So the first thing I'm going to do is rewrite that as 2 sine of x over cosine of x times cosine of x dx. I still have a lot going on, so I'm going to move that 2 to the front, which I don't usually do, but I've got so much on top and so much on bottom. I'm going to rewrite this as 2 integral sine of x over cosine x dx. Now here's where we get to have a little bit of fun with trig. Sine of x over cosine x. If I were to rewrite that as sine of x over cosine x multiplied by 1 over cosine x dx. So I'm not changing anything yet. I'm just rewriting it. That becomes 2 integral sine of x over cosine x. Well, that's tangent of x. And 1 over cosine of x is secant of x dx. So I'm not sure yet if that looks a little bit nicer, but if I go back to my trig derivative rules, I took the derivative of some function and I ended up with tangent x secant x. Well, if you look at your differentiation, if I take the derivative of sine, I get cosine. Derivative of cosine, negative sine. Derivative of tangent, secant squared. But look at this one. If I take the derivative of secant of x, I end up with secant x tangent x, which is exactly what I have right here. Which means the integral of secant x tangent x is just secant of x, which is kind of cool. So this becomes 2 multiplied by the integral of tangent x secant x is just secant x plus c, which becomes 2 secant x plus c. So this messy looking integral, once you break it up and simplify it, you actually end up with a pretty nice answer, 2 secant x plus c. So these trig functions, again, those are ones that you're going to want to remember going forward and backwards. It's going to help a lot. We'll have them up on the wall. They're in your notes. But those are things that you're going to want to start working on memorizing, which you guys are way better at than I am. But maybe we'll do a quiz in the next couple of weeks covering some of that. Okay, just more examples. Let's keep going with these. These ones I like because it wants me to not just integrate, but it wants me to find a specific solution. Okay, up to this point, we haven't found specific solutions because it hasn't given us this part, f of 2 equals 3. So basically, it's asking me to integrate, but it doesn't want me to just have a plus c at the end. It's giving me an initial value that I can use to find my c. So first thing I'm going to do is I'm going to integrate f prime of x, which is integrating 5x minus 2. So the integral of 5x minus 2, my x goes up to x squared, and I've got a 5 in front, but I also have to multiply by a half because of that x squared. And then, oh, that's a minus. And then that becomes minus 2x. I just have to add an x to a constant, remember, and then plus c. So this becomes 5/2 x squared minus 2x plus c. Now here's the cool part. This is my original function, f of x, kind of, other than this c value. But it tells me that when I plug 2 into my original function, I get a 3 out of it. So I can replace my f of x with 3 whenever I plug in a 2 where my x values are. So I'm going to plug a 2 into all of my x's, and I know my answer is going to be a 3. So this becomes 3 equals 5/2 times 4 minus 4 plus c. So 3 equals 5/2 times 4, that's just 10, right? Because the 4 and the 2 simplify, this becomes 2. So 5 times 2 is 10 minus 4 plus c. So 3 equals 6 plus c. So when I minus 6 from both sides, c is equal to -3. And I know I went through that algebra really fast, but you're just solving for c, right? You plug it in, solve for c. We don't need to go through that slow. You can pause and catch up if you need to. But now that I know what my c value is, my final answer is going to be f of x equals 5/2 x squared minus 2x, and instead of a plus c, I get to put a -3, because that is my value for c. So that is my specific solution. It's not a general solution. It's a specific solution because it tells me an initial condition, so I can solve for c. So doing this one, I like this one as well, because we get to do our antiderivative twice. It tells me that f double prime of x is cosine x. Then it tells me that f prime of pi is -2, and f of pi is -1. And it wants me to find f of x. So the integral of f double prime of x equals the integral of cosine of x. So going backwards, what gives me a derivative of cosine of x is just sine of x. And then I've got to remember my plus c. Don't forget that part. And then from here, so this is, when I take the integral of f double prime, I get f prime. So f prime of x equals sine x plus c. But it tells me something about f prime. It tells me that if I plug in a pi, I get out a -2. So this is -2. This is sine of pi plus c. And the sine of pi, if you think about your unit circle, pi is straight to the left, and the sign at that value is 0. So -2 ends up being equal to c. So my f prime function isn't sine x plus c, it's sine x plus -2, which let's just write that as -2. Now I got to integrate again. So the integral of f prime of x is just f of x. The integral of sine of x, so going backwards to get sine, it comes from cosine of x, but it's a positive sign. So I've got to do negative cosine of x. And then the integral of -2 is -2x. And then don't forget you have a plus c value. But again, it tells me that f of pi is -1. So if I plug in pi right here and right here, f of x becomes -1. So -1 equals negative cosine of pi minus 2 pi plus c. Now the cosine of pi is -1 minus 2 pi plus c. So this is -1 equals +1 minus 2 pi plus c. If I minus 1, I get -2 equals -2 pi plus c. And to get c alone, I'm going to add 2 pi to both sides. So -2 plus 2 pi equals c, which looks really messy, but that's okay. That's a constant, right? Negative 2 plus 2 pi, you could plug that in and get an actual number, but I don't want to do that. It's not going to be a nice number. I'm going to leave it in this form, but I do need to plug it back in to my f of x. So my original f of x equals negative cosine of x minus 2x, and instead of my c value, I'm going to plug in negative 2 plus 2 pi. That would be my f of x function, my original function. All right, so just if you're feeling good about this, you're welcome to go ahead and get started. But I'm going to do 3 more examples just because they're things you don't see a lot. And I mean, we've done quite a few of these, but I think the more examples of going backwards, the better. So this integral of negative 5 over root x, I'm going to rewrite as the integral of negative 5 times x to the negative 1/2 dx. This I changed to x to the half. I moved it up and made it negative 1/2. I feel like we did almost this same problem. Now, when I integrate, this x to the negative half has to go up by 1, so that becomes x to the 1/2. And I still have a negative 5 in front. But now because I went up to a half, I've got to multiply by the reciprocal of a half, which is 2 over 1. And then don't forget to add your c. So 2 times negative 5, that's negative 10. X to the half I can write as root x if I want to, plus c. Or leave it as negative 10, x to the half plus c. Those are both great answers. Just know that they're the same thing. All right. Okay, integral of t squared plus 2 cubed dt. Now, we haven't learned u substitution yet, so, which will make this a little bit easier, but right now, I'm integrating with respect to t. That tells me what my variable should be. But before I do, I really need to expand out t squared plus 2. So if you remember secondary math 3 and your Pascal's triangle, then t squared plus 2 to the 3rd power, I'm going to have a 1 and a 3 and a 3 and a 1 in front. And then I'm going to start with t squared to the 3rd power. And there's no 2. And then I'm going to add 3 times t squared to the 2nd power. But now I've got to introduce the 2. Then I'm going to add 3 times t squared to the 1st power, and this time my 2 is going to be squared. And then I'm going to add 1 times 2 to the 3rd power. And I still have to take the integral of all of that. So simplifying, t squared to the cubed, this is the integral of t to the 6, plus 3 times 2 is 6, t squared squared is t to the 4th. 3 times 2 squared is 4, so this becomes 12t squared. And then t cubed is just 8 dt. So now this just becomes, I'm just taking the integral of all of these separately. So t to the 6, I need to raise that to t to the 7th, which means I need to multiply it by 1/7. Then I'm going to add, t to the 4th becomes t to the 5th, but then I need to multiply, there's a 6 in front, but I also need to multiply by 1 over 5. Then I've got t squared, which needs to go up to the 3rd. I've already got a 12 in front, but I also have to multiply by a 3rd because I raised my t squared up to 3. And then the 8, that one's easy because that just becomes 8t. And then don't forget your constant. So this one becomes t to the 7th over 7 minus 6/5. Nope, that's not a minus sign. That's a division sign. Sorry about that. So that just becomes plus, oh, come on, pen, plus 6 over 5 t to the 5th plus 12 over 3, that's just 4 t cubed plus 8t plus c. And I can't go beyond that because I don't know. If I knew what my original like if I knew that f of 3 was equal to 4, I could plug that in to my t values and figure out c, which would, wow, that would be a mess with all those exponents. But I don't. So this is as far as I can go. Okay, now x to the 4th minus 2 over x squared. If I rewrite that, let's change colors here for a minute, as the integral of x to the 4th minus 2 raised to the x to the negative 2 dx. Now I can distribute that x to the negative 2. So this becomes the integral of x 4 plus negative 2, that's 2, minus 2x to the negative 2 dx. Now integrating is pretty easy. This x squared, we might need to move over this way. The x squared goes up to x cubed, but I need to multiply by the reciprocal 1/3. And then I've got minus, maybe, well, yeah, let's write the minus now. This x to the negative 2 goes up to x to the negative 1. And I've already got a negative 2 in front, but I also have to multiply by the reciprocal of negative 1, which is just negative 1. So that negative 1 and that negative 2 are going to multiply together. And then I have my plus c. So this becomes x cubed over 3, or 1/3 x cubed is fine, plus negative 1 times negative 2 is positive 2. And if you wanted to move that x to the bottom, then your answer could look something like that. Or if you left it 1/3 x cubed plus 2x to the negative 1 plus c, that's also correct, but this one's on the right is definitely more simplified.